This is the notes for section 5.3 for calculus. What we've talked about so far in this section is this idea of a higher derivative, second, third, fourth derivatives, which just means you keep on taking the derivative of a derivative. So this lesson here is talking about the application of a second derivative, what the second derivative tells us. So when the whole point of the chapter is talking about just the characteristics of functions. What do the graphs look like? What are the characteristics they have in them? For what x values is the function doing this thing or that thing? And one of the things that we talk about is this idea of concavity. It just kind of describes the shape of the graph. So the textbook that we're getting all this stuff from, that we're following along with, they talk about this idea of holding water or spilling water. And that it works for most graphs. But the idea here, concave up, is this section here. If you were to pour some water in there, the graph would hold that water. That would be concave up. Same thing happens over here. That's also concave up. The idea of concave down is this part of the graph here, where the water, if you poured water into it, it would spill out. Same thing. This section over here would be the concave down as well. So that's just the look of a graph. All right. Another thing to look at to help determine if it's concave up or down, it just kind of depends on some functions. Sometimes that idea of holding water doesn't work very well with the look of the graph. So what you can do is look at the tangent lines. When it is concave up, that tangent line is going to be below the function. When it is concave down, the tangent line will be above the function. It's just another way to try to recognize concave up or down. Usually, it's not a big deal. Just like we talked about with increasing and decreasing, there is a point where the graph changes from increasing to decreasing or the other way around. That was called a critical number. We have the same concept here with where the graph changes its concavity, where it goes from concave down to up, as in this graph. And that is called an inflection point. Now, the key thing here is it is a point. You can have a graph where the graph changes concavity, but what you might have is like the idea of a vertical asymptote. So if you had a vertical asymptote, say at x equals 2, this part of the graph is concave down, but this part of the graph is concave up. There's not a point where this graph is changing concavity. It's changing concavity at that vertical asymptote, but that's not a point. So in this graph, there would be no inflection point. But it still changes concavity. So with this graph, the big blue one here, there's that point where it's changing from concave down to concave up. That would be the inflection point. All right, so just some looks at the graphs. What we have here is the different looks of concave up or down depending on if the function is increasing or not. So you may want to just hit pause, kind of just study the graphs. Here's how, looking at this graph, this is always concave upward here, but this part of the graph is decreasing, this part of the graph is increasing, but it's still, both of them are concave up. So we're just looking at how the graph looks with different concavity. Okay. So, to figure out if it is going to be concave up or down and make that connection to the second derivative, got these logical thought steps here. So, the first derivative, what that told us was about the function increasing or decreasing. Slopes of the tangent lines kind of describe that pattern. The second derivative, a derivative is a rate of change. So, if the first derivative is telling us about the slopes of the tangent lines, and then we go talk about the second derivative is the change in those slopes. Okay? Second derivative is going to tell us about the change in these slopes. So, looking at this graph, this is concave up. All right? But if you look at the slopes of the tangent lines, again, first derivative tells us slopes of tangent lines. We got a negative slope as the graph, as we always read left to right, going from the negative slope to a zero slope, and then the tangent line there has a positive slope. Slopes are increasing. Okay? If you go from negative to 0 to positive, that's going up. So the first derivative tells us the slopes of the tangent lines. The second derivative is the change in these slopes of the tangent lines. So when the slopes of the tangent lines are increasing, that was our concave up. All right, and so what that's telling us, just like when we talked about increasing and decreasing, with the first derivative, when the first derivative was positive, the function was increasing. All right, the second derivative here is telling us about the change in the slopes of the tangent lines. Well, they're increasing. So what that means, same application, it means the second derivative would be positive because the slopes are increasing. And this is the key thing here. Concave up, second derivative being positive. Okay, looking at this graph, obviously, looking at it, it's concave down. But first derivative gives us these slopes of the tangent lines. The second derivative is the change in the slopes. Positive, down to 0, down to negative. So that's decreasing. And so just like we talked about with the first derivative, when the first derivative was negative, the function was decreasing. First derivative here gives us the slopes of the tangent lines. The second derivative is the change in these slopes. So the second derivative, because these slopes are decreasing, that tells us the second derivative is going to be negative, which implies concave down. So that's what we're looking for. Okay, so test for concavity. First thing, you got to have a couple things in place. First and second derivatives must exist at all points. So you just got to be able to find that derivative. Now, this is, again, the idea here. If the second derivative is greater than 0, meaning it's positive, on an interval, we got the function. That's the key things. We're describing what the function is looking like. If the second derivative is positive, the function's concave up. If the second derivative is less than 0, meaning negative, on that interval, the function is going to be concave down. Okay? So this is the process that we need to find. We need to figure out when is the second derivative positive, when is it negative. That tells us concave up or down. Where does it change concavity? That was this inflection point. So just like we talked about with the critical numbers, okay, the inflection point is where it's changing concavity. We're dealing with the second derivative. This is what we're looking for. To get the inflection points, we're looking at the second derivative equaling 0 or an x value where the second derivative is undefined. So this is what we need to figure out. The question is going to be asking, here's a function. What is the inflection points? What are the intervals where it's concave up or down? And so we need to find those inflection points when the second derivative is 0 or undefined. And then, just like we did with increasing or decreasing, we go to the second derivative and test some numbers on an interval. Second derivative positive, concave up. Second derivative negative, concave down. So let's take a look at an example here. Find the intervals where this function is concave up or concave down. Find the inflection points. So you got to start with finding the first derivative. We really want to get to the second derivative, but we got to find the first derivative first. So we get 4x cubed minus 24x squared plus 36x. And I'm just going to go right to the second derivative. 12x squared minus 48x plus 36. All right, so we got our second derivative. Now we're looking for those inflection points. So our second derivative is just a quadratic. There are no values where this thing is undefined, but we also need to look at any x values that make the second derivative equal to 0. We're looking for those inflection points. So when we set this quadratic equal to 0, the first thing I notice is 12 is a common factor. So I'm going to factor it out. That gives us x squared minus 4x plus 3 equal to 0. That quadratic that's left over factors x minus 3, x minus 1, which gives us zeros of 3 and 1. So these are our inflection, not necessarily points. Actually, yes, because we don't have any vertical asymptotes, these are our inflection points. So now, what we need to do, with those x values that we just found, we go to the number line, and that's going to create some intervals. So we got 1, and we got 3, and we are going to test some numbers. That 3 didn't write very well. So I'm going to test 0, 2, and 4. Those are the numbers I'm going to test. We're looking for the second derivative being positive or negative. So f double prime of 0. When we plug in 0 into the second derivative, we get a positive 36. And I don't really care about the number. I just care about positive or negative. Okay. When we plug in 2 into the second derivative, I'm going to plug that into the factored form here. 2 minus 3 is a negative. 2 minus 1 is a positive. So positive 12 times a negative times a positive, that is a negative value. And then, don't care about the number, just looking for positive or negative. F double prime at 4 to test that last interval. Plugging in 4 into this factored version here, positive, positive, positive. I'm just plugging in 4 here and here. Positive number times a positive number times a positive 12 is going to be a positive value. Okay, so we have our intervals. We know when the second derivative is positive or negative. So our answer is here. Question 1 of the inflection points. Technically, we should be figuring out the coordinates. I'm okay with just listing the x values. Okay, if we did want to list the coordinates, we would have the point 1, and then it's a point on the original function. So we would plug that x value into the original function. There's one inflection point. The other one happens at an x value of 3. Plug it into the original function. All right, now, we're listing intervals, just like with concave up. We're listing intervals, just like we did with increasing or decreasing. So, when the second derivative is positive, we got concave up. That was starting at this x value of 1, less than that. And we also have this interval starting at 3 going more positive, so x value is greater than 3. And the last one is at concave down. That happens when the second derivative is negative. That's this space in between 1 and 3. So x value is greater than 1, less than 3. And this is what we're looking for. We find the second derivative. The inflection points happen when the second derivative is either undefined or when it equals 0. And you got to look at both. Sometimes you only get a value from one over the other. And then you go to the number line. You're plugging in some interval values, looking for the second derivative being positive or negative. That is all. Bye.